Since ancient times, humans have gazed at the sky and admired the moon, always seeing the same face. But why do we never see the other side? The answer lies in a fascinating phenomenon called synchronous rotation. The moon spins on its own axis at the exact same rate that it orbits around Earth. This means that, as it travels through space, it takes precisely the same amount of time to complete one spin as it does to complete one orbit around our planet. This perfect balance isn't a coincidence. It's the result of Earth's gravitational pull, which gradually slowed down the moon's rotation over millions of years until one hemisphere became permanently fixed facing us. This process is known as tidal locking. The outcome is that the other hemisphere, the so-called far side or dark side of the moon, remains invisible from Earth's surface. However, this doesn't mean that side is always in darkness. In reality, it receives just as much sunlight as the side we can see. What truly makes it mysterious is that, for centuries, it was a complete enigma for humanity. We only caught our first glimpse of what lies there when we sent spacecraft beyond our planet. But how did we finally discover the existence of that hidden hemisphere? In the next segment, we'll explore the breakthrough moment when technology allowed us to peer beyond our limits and uncover the first secrets of the moon's far side. For centuries, humans could only imagine what the far side of the moon looked like. From Earth, we always see the same face, as if the satellite were hiding an unreachable secret. But how did we discover that a completely unknown hemisphere existed? This mystery began to unravel thanks to technology and scientific curiosity. In the mid-20th century, humanity managed to send space probes capable of orbiting the moon and photographing what had never been seen. The Soviet Luna 3 probe was the first to succeed, sending back blurry but astonishing images of the far side. For the first time, scientists saw a surface covered with deep craters and rugged mountains, unlike the familiar face we knew so well. The discovery shocked the world. The far side of the moon was more rugged, with fewer plains and more impact scars. These images revealed features like the Tsiolkovsky crater, filled with dark lava, and vast basins such as the South Pole Aitken, which sparked new questions about the moon's origin and evolution. Since then, each mission has added details that were once only speculation. Knowing that the moon has such a different hemisphere, hidden for so long, has inspired generations of scientists to search for answers among its mysteries. And it's within those deep, ancient craters that the secrets of the moon's past await discovery. What mysteries do these massive impacts conceal? In the next segment, we'll delve into the most impressive craters and the traces of time on the far side. So far, we've explored why the far side of the moon remains hidden from view and how astronomers first uncovered its existence. Now it's time to delve into one of the most captivating features of this enigmatic hemisphere: its craters. The far side of the moon is home to some of the deepest and oldest impact craters in our solar system. The most remarkable is the South Pole Aitken Basin, a colossal scar stretching about 2,500 kilometers across and plunging up to 13 kilometers deep. This immense structure was formed by the impact of a massive celestial body, but recent studies reveal that the collision was more complex than previously thought, and the exact cause remains a mystery. What is certain is that its size and age make it an invaluable record of lunar history. Another iconic crater is Shackleton, located near the lunar South Pole. Its depths have remained in total darkness for possibly billions of years. Thanks to advanced technology, like ultra-sensitive cameras aboard space probes, we've recently captured unprecedented images of its interior, areas untouched by sunlight. The extreme cold and perpetual shadow mean that, theoretically, water ice might exist at the bottom of some of these craters, although evidence is still inconclusive. The abundance of craters on the far side stands in stark contrast to the visible side, where ancient scars are hidden beneath vast seas of lava. This striking difference helps scientists unravel the moon's geological evolution and inner workings. But these craters hold more than just clues to the past. In our next segment, we'll uncover the mysterious signals detected in this region, signals that continue to challenge our understanding of the Moon. In the vast silence of the Moon's far side, mysteries aren't just hidden in rocks and craters. They also echo through the signals that come from this unexplored realm. Ever since humans began sending probes and satellites to orbit the Moon, instruments have picked up radio emissions and magnetic anomalies that have intrigued scientists around the world. One of the most fascinating signals was detected in the South Pole Aitken Basin, a colossal impact region we've already discussed for its extreme landscapes. Instruments from several missions have recorded low-frequency radio emissions there, which are difficult to explain using only known natural phenomena. These emissions have become a focus of study, since the far side's lack of atmosphere and its shielding from Earth's constant electromagnetic noise make it an ideal natural laboratory. But that's not the only surprise. Sensors mounted on lunar orbiters have also identified areas with unexpected magnetic anomalies. Even though the Moon doesn't have a global magnetic field like Earth, certain regions on the far side display local magnetic remnants, especially around major impact craters. These leftover fields could hold clues to ancient lunar processes or to materials delivered by asteroids and comets. Every signal we detect, whether it's an unusual frequency or a magnetic oddity, offers a key to understanding the Moon's past. These discoveries are also helping scientists develop advanced technology for future robotic and human missions. Could impacts on the far side be the source of some of these strange signals? In the next segment, we'll reveal how cosmic collisions have left deep marks and traces that scientists are only now beginning to decode. At first glance, the far side of the Moon appears to be a chaotic landscape, covered in ancient scars. Yet each crater tells a chapter of the Moon's story, and the impacts recorded there hold vital clues to the satellite's deepest evolution. Among these giants, the South Pole Aitken Basin stands out as one of the largest and deepest craters in the solar system. It was formed by the impact of a colossal asteroid, powerful enough to pierce the lunar crust and expose materials from deep inside that would otherwise remain hidden. Thanks to this impact, we can now analyze fragments from the Moon's innermost layers without having to dig kilometers beneath the surface. Recent studies show that the South Pole Aitken Basin contains an unusual concentration of elements like thorium, and that the crust there is much thicker than on the near side. This reveals a strikingly different geological history between the two hemispheres. While the near side was shaped by volcanic activity, the far side was dominated by impacts. These craters not only show us when and how the Moon formed, but also explain why its two faces evolved in such different ways. Other formations, such as the Planck and Tsiolkovsky craters, provide further clues about ancient collisions and the occasional lava flows that flooded their floors. Each of these impacts left scars that scientists examine to reconstruct the Moon's most crucial chapters. As exploration continues, researchers believe these craters still hide unexpected secrets. What other signals might the far side of the Moon be keeping, especially when it comes to magnetism and its mysterious internal energy? So far, we've explored the shapes, mysteries, and impacts that define the hidden side of the Moon. But there's an even deeper enigma: its connection with the lunar magnetic field. Unlike Earth, the Moon does not have a global, active magnetic field. However, on its surface, especially on the far side, scientists have detected areas of local magnetism, almost like invisible islands. Where do these magnetic traces come from? Experts believe they are linked to ancient, violent impacts and the materials scattered by these colossal collisions. In the South Pole Aitken Basin, one of the largest craters in the solar system and located on the far side, unexpected magnetic anomalies have been discovered. These regions may be due to the presence of iron-rich minerals, meteorite remnants, or even ancient volcanic activity. The heat from impacts or volcanism could have temporarily magnetized lunar rocks, leaving traces that we can still measure from orbit today. Most intriguingly, These magnetic signals reveal clues about what the moon's interior was like millions of years ago and how it evolved after being shaped by massive impacts. Understanding these traces is essential for reconstructing the satellite's history and for planning future missions, since magnetism can influence the protection of equipment and astronauts from space radiation. Next, we'll see how some speculative theories have tried to use these enigmas to imagine even more astonishing secrets hidden on the moon's far side. The mystery of the far side of the moon has captivated not only scientists, but also those drawn to conspiracy theories. For decades, stories have circulated about alleged secret bases, artificial structures, and inexplicable signals detected by spacecraft. Images captured by missions like Luna 3 and Apollo 17 have been reinterpreted by those searching for evidence of intelligent activity on the hidden hemisphere. Many believe that the lack of direct exploration for years fueled these rumors. People point to geometric shadows, unusual patterns in craters such as Cyclic, and areas where the terrain appears almost too regular to be natural. Yet, science has shown that most of these formations result from unique geological processes and asteroid impacts that have shaped the landscape over billions of years. Popular theories suggest that governments and space agencies are hiding information about extraterrestrial bases or secret human installations. However, experts are clear. No credible evidence of artificial structures has ever been found on the far side. The latest data from missions like Chang'e 4 and high-resolution image analysis confirm that the craters and mountains in this region are products of lunar nature. Still, curiosity and mystery endure. Each new mission, each photograph, and every fragment of rock collected from the far side fuels the imagination and stirs new questions. Could future explorations turn up unexpected clues? What is certain is that the study of this region is uncovering surprising geological differences. And soon we'll see how science addresses the riddles that speculation has kept alive for so long. Until recently, the moon's far side was a virtually unexplored realm. That changed with the arrival of the Chang'e 4 mission, the first spacecraft to softly land on this mysterious hemisphere. What secrets did it uncover by directly studying the most enigmatic lunar terrain? Chang'e 4 touched down in the South Pole Aitken Basin, one of the oldest and deepest regions of the moon. There, its instruments and the small Yutu-2 rover began analyzing the surface and subsurface, sending back unprecedented data to Earth. One of the first major surprises was the remarkable difference in structure and temperature between the two hemispheres. Measurements confirmed that the far side's interior is 100 degrees colder than the near side, revealing that the moon's asymmetry goes far deeper than the surface. Chang'e 4 also found that the crust is thicker and more mountainous, packed with craters, and it detected traces of materials from the moon's deep interior. These fragments, studied from afar, suggest that the giant impact that formed the Aitken Basin brought ancient rocks to light, rocks that had never before been exposed, offering a unique glimpse into the satellite's distant past. The mission's results not only confirm that the moon is truly a world of two very different faces, but also provide clues about its origin and evolution. Yet beneath that frozen ancient surface, there are still key geological differences waiting to be unlocked. What other surprises await as we compare the far side with a familiar face we see every night? That's the next step in our lunar exploration. After exploring the deepest craters and the mysterious signals detected on the far side, a crucial question arises. Why is this lunar hemisphere so different from the one we see from Earth? The most striking difference is visual. While the near side of the moon shows large, dark patches known as lunar maria, the far side is almost entirely covered in craters and has very few of these vast plains of solidified lava. The maria formed when massive lava flows filled ancient craters after colossal impacts. In contrast, the far side experienced much less volcanic activity, leaving its surface more rugged and densely scarred by impacts. Scientists believe this asymmetry is rooted in differences in the thickness of the lunar crust. The far side's crust is much thicker, making it harder for magma to reach the surface after impacts. This explains why maria dominate the near side, while craters remain on the far side. The temperature is also notable. The far side can be significantly colder than the near side, partly due to its geography, exposure to sunlight, and the absence of maria that would otherwise absorb and retain solar heat. These differences are not just geological curiosities. They are vital clues for reconstructing the moon's early history and understanding why it developed in such an asymmetric way. Moreover, the far side hides resources and mysteries that could shape the future of lunar exploration. And that is exactly what we will uncover in the next segment. Now that we understand the geological and thermal differences between the near and far sides of the moon, a fascinating question emerges. Why does the future of lunar exploration depend so much on this mysterious and little explored region? The far side of the moon, especially the South Pole Aitken crater area, has become the top priority for upcoming international missions. Why? Its surface acts as a unique window into the moon's deep interior. Here, ancient impacts have exposed material from deep beneath the surface, allowing scientists to study the moon's inner layers without the need for complicated drilling. Analyzing these rocks could reveal secrets about the moon's origin and evolution, and explain the striking differences between its two hemispheres. But the importance of this area goes beyond basic science. The stable, shielded environment of the far side is ideal for installing radio telescopes, free from Earth's signal interference. Its cold temperatures and the potential presence of resources like frozen water at the poles open the door to future inhabited bases and to producing fuel for even more distant missions. In short, the future of the moon and humanity's next steps in space are closely tied to what we learn and build on the far side. What we discover there could reshape not only our understanding of the moon's past, but also our own destiny beyond Earth. Want to discover more secrets and challenges from the moon's far side? Subscribe to the channel and share this series so you don't miss the next episodes.